Our next speaker is Maria Eckstein. Kevin Miller was supposed to be here. Unfortunately, he couldn't join. Maria is from Google DeepMind. She is a senior research scientist at Google DeepMind with a PhD in psychology from UC Berkeley. She mainly studies the intersection between cognitive psychology and artificial intelligence, and she is particularly interested in questions that are fundamental to both fields, such as learning, decision-making, cognitive representation, and structured thought. Today, she's going to talk to us about using AI to drive mechanistic models of natural intelligence. So the floor is yours, Maria.
Thank you so much. Yeah, I'll be presenting on behalf of Kevin Miller and myself because, he couldn't make it. So what we wanted to talk to you about is how we can use AI to derive mechanistic models of human intelligence. So switching gears a little bit. And so how does cognitive science work in an era of machine learning? We think that machine learning methods can really help with all steps in the process, in the scientific process. And so if you start from a theory, I think the core of cognitive science really is to make theories of how the mind works. Like, what are the moving parts? What are the components of it? How do they all come together? What we often do is we use those theories to design experiments so we can test those theories. And machine learning can help in that process, for example, allowing us to create large-scale procedurally generated experiments. And then we run experiments, which we can do with the help of ML, to gather data sets. And we can use ML to pre-process those data sets. And we believe we can also use ML to then interpret these data and derive theories about what these data really mean. And this is what I want to talk to you about today. And so the way to think about this is that there's two big approaches of how we can use modeling. One of them is a kind of classic cognitive modeling. So what we do here is I imagine that most of you are familiar with reinforcement learning or reinforcement learning modeling. So this is what I'm talking about here. So we use a model that implements a cognitive process. And we create this model, we compare to some behavioral data that we have collected from humans. So humans do some kind of reinforcement learning task. We fit this reinforcement learning model. And what we want to do is this model will be interpretable because we know all the processes that are going on. We know all the latent variables. We know how those latent variables are related to each other. And what we want is a model that fits the data really well. So that captures all the intricacies of human behavior in this data set. In order to do that, what we usually do is we say, okay, we start with reinforcement learning. Now we say maybe humans also forget, maybe humans also do this and do that. So we modify the model, and over time we get a model that fits the data better and better and explains human behavior better and better. One problem with this approach is we never really know when to stop. So we never know when is the model that we have arrived at good enough. Another approach that we could take is to use machine learning to achieve the same goal. So what we do here is we just take any off-the-shelf machine learning model, we fit it to human behavior in the same way, and then we can also use some tricks in order to fit the data set better and better. So in order to predict human behavior better and better. But the thing that and these models have the big advantage that they tend to fit data really well. So they're really good at predicting human behavior. But the problem is that those models don't give us an explanation of why humans do what. So what we really want for a good cognitive model is a model that is both interpretable and also predictive. So what we really want is a model that explains all the intricacies of human behavior and to capture all the barriers that there is and all the things that humans do that are very interesting, but at the same time they're interpretable. So they also tell us what the mechanism is, what the latent processes are, and how they all come together. And so there's a lot of different ways that people have tried to get at this. So I'll just give you kind of a big overview of the field here. And one of them is to take those generic machine learning models and try to interpret them. For example, we can do dynamical systems analysis. We can make those plots. We can find the stable point, the fixed points, the saddle points of how those systems move through latent space and try to figure out what it tells us about humans. We can understand the representational geometry of those systems. we could study the behavior of those systems. So we fit one of those models, and then we try to understand how does it behave and why, and what does it tell us about humans. And we can also, instead of taking one of those out of off-the-shelf machine learning methods, we can also create new machine learning algorithms that are interpretable by the design. So we can tweak the design a little bit to make sure they will be interpretable. And so one approach here is a tiny network. So pretty much these are just recurrent neural networks, but they have a very small dimensionality. And what that means is it it forces the model to only encode the necessary information. And this will be very low dimensional, so it will be interpretable by design. We can use symbolic regression, so we can submit a whole data set to the symbolic regression algorithm, for example, Cindy or something like that. And instead of giving us a big black box neural network, it will give us an equation, like a physical equation for physical system, that will describe the data set and will be interpretable in that sense. We can use dimensionality reduction to plot or to understand those latent dynamics in a lower dimensional space. And one other approach that Kevin has been spearheading is what he calls disentangled neural networks. So I'll tell you a little more about this approach. So what Kevin did here is he thought about the notion of disentanglement from variational autoencoders. So what disentanglement means is pretty much, it comes from the notion of variational autoencoders. So you have an encoder, you have a decoder network, you have a small bottleneck in the middle that forces information to be in lower dimensional space. And it has a bottleneck in the middle. So pretty much what that does is, if you encode visual images, for example, the latent dimensions will oftentimes match onto the factors of your true data generating process. So say you have visual images, one latent might map onto the color, one latent might map onto the rotation of a chair, one latent might map onto the size of the chair, just because this is the most efficient representation of this really high dimensional data set. And so what Kevin did is he took those information bottlenecks and embedded them in a recurrent architecture. So here, this is just a visual depiction of his model, and what you see is different latents. So this would just be the latent variable in a cognitive model. For example, if you think about RL, this would be a Q value. If you think about Bayesian inference, this might be a belief state. If you think about an accumulator model, that might be the variable that gets accumulated. All those variables go round and round in this model. So this is trial T and trial T plus 1, trial T plus 2, and so on. And on each trial, they will get updated. And now all of those orange arrows are bottlenecks. So pretty much what this model will do is it will take a latent from the previous time step, say a value, say a belief. It will pass them on to an update function. So this function is, if you think about RL again, this would be how I update my values, or in Bayes, how I update my beliefs. And crucially, now here there are bottlenecks. And what that means is that each update function will only take a small number of those latents. In this way, each update function will be interpretable, because it will only deal with a small number of latent variables rather than all the variables the system is representing. And then once the update function has done its magic to the latents, once the update function has updated the latents, they then go and will pass on to the next trial. And before they do that, they will pass through another bottleneck, which ensures that there just aren't as many latents. So instead of having 20 different latents, you might only have 5 or 2, and that will again make the system more interpretable. And so the first thing that Kevin tried to make sure is that this actually works. And how could you make sure this actually works? What he did here is he just simulated data. So this is simulated data. This is no human behavior. He simulated data from an actor-critic agent. And all you need to know is that the actor-critic agent has 2 latent variables. One of them is green and one of them is blue. And they wiggle over time as this agent plays a reward-based task. So whenever there's a green dot, that means that the left choice got rewarded. And here, the right choice got rewarded, the left choice got rewarded, and so on. And those latent variables wiggle over time. This just describes the behavior of the system. And this agent also has update rules, which I'm just plotting here very coarsely. And now what Kevin did is he fitted his disentangled RNN to this data set. And this is the fit of this model. And what you see here is the blue latent matches pretty much exactly onto this blue wiggling line, and the green latent matches onto the green wiggling line. And this is exactly what we wanted to see. So what that shows is that if you take this disentangled RNN and just fit it to the behavior of this agent, it will give you an exact picture of how all the latent variables are moving over time. So pretty much we take this complex behavioral data set that has been generated by actor critic, and we fit this disentangled RNN to it, and we get the ground truth back. So we see exactly what are the latent variables and how do they change over time. And if you then look into this model and look at the update rules that it has learned in a data-driven way directly from the behavior, we see that it recovers those update rules very, very precisely. So in other words, what this shows is that this model can digest a really complex behavioral data set and pull out those latents and pull out the update rules that really guide that behavior. So we're really excited about that. And what Kevin did next is he tried this model out on actual behavior that we're actually interested in understanding, where we don't know the ground truth. And one of them is a two-armed bandit task. So this is the behavior of rats in a two-armed bandit task. Again, here the left choices and the right choices, rewarded and not rewarded. And what this model shows us is that there are two different latents, the blue one and the orange one. And what he showed is, or what we saw is that the blue latent captures a relative value signal, similar to RL. So only there are two arms, so it's the relative value between the two. It will go up whenever the left choice has a larger value, and it will come down whenever the right choice has a larger value, which makes a lot of sense with reinforcement learning. And then he also found this orange latent, which is something like perseverance or habit. So whenever the rat chooses left, it will choose left again, and whenever it chooses right, it will tend to choose right again. And then this method is very general because Kevin also tried it on an evidence accumulation task. So this is a task where rats hear clicks on either side, and they need to then decide which side were there more clicks on. And what he saw in this case is that there's this spring variable that seems to be an accumulator. So it always goes down when there's a click on the right side, and it always goes up when there's a click on the left side. So it seems like that would imply that rats are counting how many clicks they've heard on each side. And then there's also this blue variable that is sensory depression. So whenever the rat just heard a click, it is a little less sensitive to hearing clicks briefly thereafter. And this matches well onto the most standard cognitive model that people actually have handcrafted for this task. But again, using this approach, Kevin was able to find this model without any theory in a purely data-driven way. Okay, so coming back to this big picture, we want to find cognitive models that are both interpretable and that also fit a data set really well. Another approach that people have taken is to kind of hybridize both methods. To say classic cognitive modeling has a lot of strengths and has got us very far, and machine learning can be an additional tool in this endeavor. How can you bring both of those together? And one example is a beautiful paper by Josh Peterson et al., where they took prospect theory and replaced some components of prospect theory with neural networks in order to get a model that is just more complete, that fits the data better. And I have tried a similar idea in the case of reinforcement learning, and so I'll describe a little bit how that works. So pretty much the starting point of this method was a 4-arm bandit task. So again, humans choose between different options, so they get rewards on each trial. And I start with one classic cognitive model. So this is up here, this is an RL model, and with a classic machine learning approach to just have the two biggest contrasts. So here, this is just a visual depiction of reinforcement learning. Let me see if I can use the mouse. Yes. Oh, do you see that? Yeah. Okay, so this is just a visual depiction of reinforcement learning. So pretty much what reinforcement learning tells us is that we learn values, and on each trial, we obtain a reward, and then we calculate some reward prediction error, we update our values, and we go around the circle, we go round as we gather more information about our choices. And there also is a perseverance kernel here, which just says, if I choose an option, I'm likely to choose that same option again. And here's our recurrent neural network, which is a black box algorithm that doesn't really tell us a precise cognitive mechanism of what is going on. And so the first step that I did is I took this reinforcement learning model. I took the exact same architecture, and all I changed is I replaced all of those equations with neural networks. And then I fit the whole model to my data set again in order to understand human behavior. And what that lets us do is it lets us say, if we accept all the constraints that reinforcement learning theory imposes on the cognitive mechanism, how much behavior can we explain? Now we say any function can be fitted. This is a free parameter. The best function possible will be gathered from human behavior, but it is a generalization of reinforcement learning that can learn any function from the data that will make the model fit best. And then after we do that, we can take another step and we can say, okay, maybe some of those assumptions, some of the structural assumptions that RL makes about the cognitive architecture are not actually true. And now we can test, and people have argued that some of those are actually not true. So now we have neural networks, we can test those assumptions. For example, we can say, maybe this computation, maybe the way I process the rewards that I obtain in my task are conditioned on my current value landscape, are conditioned of what I have already learned about this task. And in order to test this, we can create an additional input to our system here. We can feed the current value landscape, the current representation back into the model in order to condition the function, the processing on this. And then we can take another step. We can go even further and we can say, maybe this is just not a memory representation that is flexible enough in order to capture human behavior. Maybe we need a more flexible memory representation. Maybe the memory representation needs to be disjoint from the action guidance. And so what it did is I fitted all of those models to a human choice data set. And here I'm just showing you the model fits of the RL model and of the neural network model. Lower is better here. And you see the pattern that I alluded to earlier, that the recurrent neural network really fits the data much better than one of those classic models. And I'm just plotting error bars here, just highlight the difference. So there's a huge difference. Typically, those black box models just fit human behavior infinitely better than those more classic models. And so what we can do now is we can try to understand what those models are doing. So here I'm just visualizing the standard RL model, and here I'm just zooming in on the value updates. I'm plotting rewards, I'm plotting values. The larger reward, the larger value, but it's also dependent on the previous value. And now what we can do is we can create this first recurrent neural network model that has the same cognitive architecture. We can look at the model fit. I was really surprised when I saw that it did not actually improve the model fit. I thought, what is going on? I thought if I make the thing more flexible, it will definitely fit better. But when we look at what this model learned to do, it makes total sense. So this model basically just recovered the reinforcement learning value update. And in other words, what this shows us is that as long as we operate within the constraints of RL actually is a really good model of human learning. And like decades of people have used reinforcement learning model in order to understand human reward-based learning. And it makes perfect sense because as long as we operate within the constraints, we recover reinforcement learning from the data. However, what we can do next is we can relax some of those strong assumptions that RL makes on the cognitive algorithm. And we can look at some of those models. And this is where we really gain substantial amounts of model fit. And if I show you the other model, this is our winning model, which actually reaches the noise ceiling. So it explains as much behavioral variance in the in the data as our black box model. And what we can do now is we can, again, look into those functions that this model learns from the data in order to get an interpretable model of human behavior. And so to wrap this up, I've shown you a few different models in this greater landscape of cognitive models that people have used. We have those classic cognitive models where we kind of handcraft equations that are theory-based, where we come up with a theory like reinforcement learning, Bayesian inference. We code that up and we say this fixed mechanism is what people do. Or there is this other, at the other end of the spectrum, there are those more generic machine learning models that are black box, that are general purpose, that we can also fit to human behavior, that are really good at predicting human choices, but they don't necessarily give us insight in what the cognitive mechanism is that leads to those choices. And people have thought about a lot of different ways of how to reach this upper right quadrant, where we really want to go, where we have models that both are interpretable and that also are predictive. And I think there's a lot of exciting future directions to go with those models. And yeah, I'd like to talk to anybody who's interested in that. And with that, I just want to thank Kevin and all our collaborators and yeah.
Thank you, Maria, so much. That's questions.
Yeah, thanks, Maria. That was terrific. And I'm convinced this data-driven model discovery is going to be important. But I'm wondering if it neglects some aspects of what people do when they design models, because often modelers have intuitions about what they want to do next or future data sets. So considerations outside the immediate data set, or just maybe like on the brain work. So they might want some kind of specific sort of neural network model. And could it be that when you use this technique, I mean, again, it looks really promising and valuable, that it might lead to, in some sense, overly simplistic models, because it's really only structuring the model on the data set at hand, which seems like really good science for that paper, but sometimes people are thinking more cumulative to the next paper, the next paper, the next study, and so forth.
Yeah, I think this is a great thought. So Kevin actually just walked in. So I imagine he might also take some questions, but I'll take this one. So yeah, I think there's a lot of different responses to that. So I think I highlighted two approaches, the disentangled RNNs and the hybrid RNNs. And I think they also live on a spectrum between data-driven and hypothesis-driven. And I think disentangled RNNs have the great advantage that they are purely data-driven. So we don't impose anything on those models, except that they need to be simple and they need to be interpretable. And so I think what you say applies there. Like, we can't put a lot of prior knowledge into them, and we don't want to, because the whole point is to be data-driven and to find the simplest model. I think for hybrid RNNs, we can do much more in that regard. Because I can actually say, in this case, I started with reinforcement learning just because it's popular and everybody knows it and uses it. But I could test a lot of other assumptions as well. I could put things in there that are brain inspired, because I do this model comparison step. And which models, which architectures I compare is completely up to me. So they require more a priori specification. They require more theory from the modeler, and they try to combine both. So I think in that way they might do that. The other thing that you said about data sets, I think is entirely true. And as long as we just use one data set and try to model the heck out of it, we will always like reach some local minima or something where we might understand that data set, but it might not generalize to other data sets. So that's exactly what the landscape looks like, where a lot of studies, one says, oh, learning rates do this, learning rates do that, and everybody contradicts each other. And I think a big problem is that A, people are using different models, and B, people are using different data sets. And so it seems like a contradiction, but it might actually just be different reflections of the same model onto different costs. And so I think in order to solve that, we can use we can make better data sets. So we could make data sets, procedurally generated data sets, say, that don't just test one 4-arm drifting bandit task, but maybe also 2-armed and 3-armed, and not just drifting, but also jumping. And so we can generalize over the task that we're testing, rather than having one dot in the space of Vanitas, we could capture the entirety of Vanitas. And that, I think, is when we will really need some more powerful models like this, because then we will want to be a little more data-driven and pull out the variance there. Yeah. Okay. More questions? Yeah.
Thanks, Maria. That was great. I was wondering from your hybrid model, can you verbalize what you've learned? Like, what is the interpretation of
Yeah.
your enforcement learning and how humans do it that we didn't know before? So
Yes.
I understood what you said about what is still true,
Mhm.
but what is not true that
Yes.
we could learn.
Thank you so much for the question, because I didn't have time to go into that. But that's actually the most interesting thing, I think. So I think what you learned is pretty much one strong assumptions that RL makes is that you have this one variable, this one hidden variable, which are your values, and they are the heart of everything. The values are what contains all the memory of the system. So it's a condensed representation of the previous history of rewards and of previous actions. And it's low dimensional, and the values are what guides immediate choice. And so they carry a lot of weight, they do a lot of different things. And pretty much what this model tells us is that we need to break those roles apart. We need to treat them separately. So pretty much what this model is saying is that we have one variable here that guides choice, and we have another variable here which contains the memory, and those need to be separate. So pretty much what it says is you can't use you need to remember some things about the past that don't influence your current choice. That doesn't make sense. So pretty much the choice guidance needs to be separate from the memory representations. Where values try to do everything, they both tell you what you do and they tell you everything that's happened. This model says, no, your memory of the past, your representation is separate from your guidance, your action selection. So I think this is one big aspect. It pretty much says there are no values. Values are the core of RL. It pretty much says there are no values. You need to have a separate memory and you need to have a separate choice process. They need to be separate. They can't rely on the same representation. And another thing that it says is that the way we process rewards now, it looks very different from the way RL tells us to process rewards. So RL does this like very beautiful, simple, linear thing, whereas this model says, no, we do something that's much more complicated. So you could be in a state like this yellow state here, where you respond pretty similarly, no matter if you get 100 points or 50 points or 25 points. So this is a state of low reward sensitivity. But then this model could flip into a state of high reward sensitivity, where the difference between 100 points and 75 points really is huge. So it can go into different states, say, to make choices.
Thanks. Super interesting.
Could you just speculate or say what your thoughts are about the distinction between memory and decision processes, humans versus large language models?
I wish I could say something about that. Unfortunately, I can't because I haven't done the study, but I think it would be super interesting. And people have actually started doing things like that, where they have an LLM, let it play down the task, and then fit some cognitive models to it. So people have done it for the two-step task, for example, and seen, oh, large language models seem to have you seem to use both model-based and model-free mechanisms in a similar way to humans. So I could imagine doing something similar to that. So we could literally ask a large language models to do the same task and then fit the same models and then see if they have the same components here. Yeah, I don't know what would come out. It would be interesting to see, I think.
Thank you so much,
Thank you so much.